In this module 8.4, we are going to be looking at strategies for doing nonlinear filtering, approximate nonlinear filtering using the so-called ensemble or reduced rank approximations. So this has come to be called ensemble or reduced rank filters. Let's quickly review where we are. For the LQJ problem, when the system is linear, observations are linear functions of time, when I am using least square criterion, and when all the distributions are Gaussian, we could derive the exact filter equation for the mean and the covariance of both the forecast and the analysis. But when either the system is nonlinear or the observations are nonlinear or both are nonlinear, we are going to have difficulties. We saw the difficulties in the variety of ways. The difficulty essentially arises from the fact that Gaussian, all the other distributions other than Gaussian distributions are not or cannot be specified simply by the first two moments. So if you get, so our aim in nonlinear filtering is to work in the infinite dimensional space of distributions. So what is the forecast distribution? What is the analysis distribution? How do the forecast distribution, analysis distribution interact with each other? How do we update these two distributions? We derived sequential updating scheme for updating the forecast distribution as well as analysis distribution exactly using Bayes framework, much like we did in the linear framework. So what is the difference? In the linear framework they are finite dimensional, there are only two variables, mean and the covariance. But in the nonlinear filter it is infinite dimensional because we are trying to give an updating scheme for the distribution themselves. So given the attendant numerical, so it is not that we do not know how to solve nonlinear problems, we know theoretically how to solve it, we know the exact solution. So what is the problem, what is the challenge? It is very difficult to be able to compute the exact forms of these distributions, they can only be handled numerically. So given this difficulty, we then moved on to computing approximate moment, approximate moment dynamics. So we derived expressions for the evolution of the mean and the covariance. In that juncture we met with the so-called closure problems, which are typical of any and every nonlinear systems. And as a consequence we saw zeroth order filter, which depends on linearist approximation. We talked about first order filter, which has come to be called extended Kalman filter, and we also talked about second order filter, which is a little bit more accurate than the first order filter. While these are meaningful approximations have been used in several walks of life, these approximations are computationally no less severe for geophysical applications, because in geophysical applications the size of the problem easily of the order of million. So we have to deal with vectors and matrices which are of size million or more, with the ever increasing interest in finer grid. The number of grid points in a typical global model may reach 1 billion very soon, and so the desire to have a more accurate representation using a computational grid with a smaller grid size is becoming one of the challenges, and these challenges cannot be meted out until we have powerful computers. So given all this challenges all around us, the reduced rank filters based on ensemble idea, which is essentially a Monte Carlo idea, has become very popular. It is very simple. You don't need to write an adjoint. You don't need to solve any least square problems. The basic idea is you have a model code. If you have a multiprocessor, you pick several initial conditions from an appropriate distribution, run the model forward in parallel, and once you spit out the forecast from say 50 models or 50 model runs, from 50 model runs of the same model code but starting from different initial conditions. So you will get a forecast ensemble which is generated from an initial ensemble. Once the forecast ensemble is generated, the forecast mean and the forecast covariance are essentially calculated as a sample mean and a sample covariance of this forecast ensemble. After having created the forecast ensemble, we then integrate the observation with the forecast ensemble to create an analysis ensemble, and from the analysis ensemble we again start the model moving forward, creating a forecast ensemble. So this notion of being able to create a forecast ensemble, from there an analysis ensemble, and starting the model forward again from the given analysis ensemble is a sequential way of thinking. So we are still remaining within the sequential framework. The only difference is that we never look back. We simply keep moving forward not on one simple model run but from an ensemble of model runs. So that is the basic idea. Where does the reduced rank come from? The given size of the problem, let us say 1,000,000 for example, let us fix it. So in order to be able to ensemble based computation of covariance matrices which are full rank, I may need to run of the order of 1,000,000 ensemble members. Running 1,000,000 ensemble members is impractical in today's technology. So what do? They pick a small sized ensemble, 50, 100, 200. So by creating 200 ensemble members of a model run, I am going to basing simple statistical principles to be able to estimate the mean of 50 ensemble members and the covariance using 50 ensemble members. The basic statistics tells you if you have the number of samples of the order of 50, if you are trying to compute the covariance matrix, the maximum rank of the covariance matrix can be no more than 50. So we are trying to approximate a matrix of rank 1,000,000 by a matrix of rank 50 or 100 or 200. That is what is called the reduced rank approximation. So if we can capture some of the important modes of behavior of the model, maybe we can very carefully approximate the forecast covariance, analysis covariance, analysis mean, forecast mean, and keep going forward. So this is a class of approximation which is computationally simple, which is scalable. The scalability largely depends on the size of the problem and the power of the computers. So because of this flexibility, this class of ensemble based methods have become very popular in many of the operational centers around the world. So in this module we are going to provide a very broad overview of the current methodology that has come to be known as ensemble method or reduced rank filters. So what is the basic idea? Let fx be the density of a random variable x. So x is a vector. Let x be a vector in Rn. F of x is the probability density. Let the mean of the random variable be mu and the variance of the random variable. Oh, did I say f of x is equal to no? Oh, no. We will simplify this. Let us assume we have only a real random variable to start with. Let us assume I have a real random variable x and f of x be the density function for the real random variable with mean mu and variance sigma square. Let x1, x2, xn be the n IID samples. What is IID sample? Independent samples that are drawn from the same distribution f of x. The distribution remains the same. I'm simply, so you can think of the distribution as a black box. you ask for a number, it will give you I running from 1 to n. So you can draw n such sample from the same box that represents the distribution of fx. That's called IID samples. So if I have n members of the IID sample, I can compute the mean, I can compute the sample covariance, and from our class on statistical estimation, we have already shown that this estimator for the mean and this estimator for the sample variance are unbiased estimates. So this is x bar n is an unbiased estimate of mu, and s square n is an unbiased estimate of sigma square. Very simple basic statistics. This is the first one you probably learn in any course in fundamental statistics. What are the basic properties of these estimates? The probability that the estimate of the mean using n samples differs from the true mean by a magnitude more than epsilon tends to 0 as n tends to infinity. So what does it mean? The sampling distribution of x bar n. So x bar n is a random variable, it is an estimate. Estimate is a random variable. The estimate has a distribution. The estimate has a distribution whose mean differs from the original mean mu by a smaller and smaller and smaller quantities as n, the number of samples, goes to infinity. That is what is called the consistency condition that we have seen earlier. Likewise, if I consider the estimate of the sample covariance, the sample covariance estimated using the formula in the previous page differs from the true variance by a quantity epsilon. The probability of that event happening goes to 0 as n goes to infinity. So what does it mean? Both the sample mean and the sample covariance become closer and closer, ever closer to the true mean and the variance as the number of samples goes to infinity. This is a very simple fundamental fact. What is another way of saying this? The variance of the sample mean, so sample mean is random, therefore it is the variance, is sigma square n. So sigma square n is the square, sigma square n is the variance of the sample mean, and that goes to 0 as n goes to infinity. That is one of the statements that is captured in the first line. The second line is also captured by this expression for the variance of the estimate of the sample covariance. You can see as n goes to infinity, these two goes to 0. The standard error in the estimate is equal to I should say the standard error is equal to sigma by n, which is the square root of the variance, and that is proportional to, so I will simply say the following, that is proportional to 1 over n. That is proportional to 1 over n. So what does it mean? The standard error, which is the square root of the variance, is sigma over n. Sigma over n is proportional to 1 over n, and 1 over n goes to infinity as n goes to infinity. So that is another way of saying these things. In fact, many of the fundamental ideas of ensemble filters rests on this consistency criterion of basic estimates of both the mean and the variance. So what is the only difference? In the context of meteorological system, we are going to be concerned with random vectors instead of random variables, but whatever holds for random variables also holds for random vectors, and that is what we will exploit. Another tool that we need is the following. Suppose x is a random variable, x is a normal random variable with mu as the mean and sigma as the covariance. I can do a transformation. What is the transformation? First, compute the Cholesky factors of sigma, which is L transpose. Please remember, we have already talked about Cholesky decomposition. The Cholesky factors are also called square roots. So let sigma is equal to L transpose, where L is called the square root of sigma, L is also a lower triangular matrix. We have already given an algorithm when we were dealing with numerical methods for solving static deterministic inverse problems. We had given the algorithm for Cholesky decomposition in great detail. So given sigma, I should be able to find L very easily. Now let y be a standard normal variable. Let y be a standard normal variable. So in this case, what is x? X is a vector, mu is a vector, sigma is a matrix, L is a lower triangular matrix which is a square root of sigma, y is a standardized normal variable which has mean 0 and identity as the covariance. Now I can relate x and y through the relation 3. So what does it say? Y is equal to L inverse x minus mu, or x is equal to mu plus Ly. So this transformation relates a unit normal random vector to a general normal vector with mean mu and covariance sigma, and the verification of the third statement is given in the box on the right hand side. You can easily verify that. So what does this tell you? If somebody gives you a random variable, so how are we going to be using this? We have talked about what's called whitening filter. What is a whitening filter? In general, sigma is a matrix with element sigma ij. Sigma ij, what is the value of that? It is the covariance of xi versus xj. So in principle this need not be 0. Therefore if I have a vector x whose mean is mu and covariance is sigma, the elements of the covariance matrix may be correlated, and the correlation is given by, or may be correlated, the covariance between them is given by sigma ij. But when the covariance matrix is I, the diagonal elements are 0. So y is a Gaussian random vector whose components are uncorrelated. X is a Gaussian random vector whose components are correlated. So 3 gives you a transformation from a correlated random vector to uncorrelated random vector, or uncorrelated random vector to a correlated random vector. So the transformation from x to y is called whitening transformation. X to y is called whitening. Transformation. Why this is called whitening transformation? White noise doesn't have any correlation. So y does not have y has components which are uncorrelated. So considering a given correlated vector, how do you convert it into uncorrelated vector? We have utilized this whitening transformation in the context of Potter's algorithm when we did the square root version of the covariance square root version of the ensemble filter in a couple of days, in a couple of classes ago, in the same module. Now with these two this is all what you need in principle to be able to do an ensemble method. So let us assume I have a model, stochastic model. So here I am assuming I have a stochastic model. That means I have a model code. Somebody has developed the model code. I have an observation. X naught has the standard one. You can say x naught is equal to, is normally distributed the mean m and covariance p naught. Wk is mean 0 and covariance qk, and Vk is mean 0 and covariance rk. We also assume x naught, Wk and Vk are uncorrelated. So these are the properties of the model. These are also properties of the observation. And this is the basis. You need to be able to give all this information to do any stochastic data assimilation scheme, in particular Kalman filter. So this corresponds to the following: the model is nonlinear. I have simply assumed the observations are linear functions. I could have assumed the observations are also nonlinear. simply I am giving a mix of many things, linear with linear, nonlinear with nonlinear, nonlinear with linear. So lots of combinations of choices between models and observations. So how does the ensemble method start? So I have a model, I have observations, I have the underlying properties, I have the basic facts already described. So what do I need? Initially I am given the initial distribution x naught, initial distribution of x naught, which is m mean and p naught. So first do a Cholesky factorization of p naught, which is s naught transpose. Please remember Cholesky we have already seen. Let y naught I running from 1 to n be the n samples drawn from the standard normal distribution. Look at this now, there are two indices now coming in here, y0, this is the time index, we have to be very careful, and this is I, this is the ensemble index. Then we will have a representation for the forecast or the analysis. So you can see I need time, I need analysis or forecast, I also need to keep track of which member of the ensemble I am going to be dealing with. So each of the variable will be loaded. There is a time index, there is an ensemble index, and there will be an index or a notation for whether I am concerned with forecast or analysis. Once you separate all these things, keep in your mind how a particular notation is formulated. In our notation, time is always subscript. Ensemble index, I put it in the stomach. I wanted to go back. If I have a variable x, what are the different ways of notating? I can say x of t, that is stomach. I can put it in the leg, that is subscript. I can put it in the head, that is forecast. So instead of t I will change it to, instead of t I will change it to I. So this is the ith member of the ensemble at time k, but it is a forecast time. So there are three ways of notating to be able to distinguish different quantities. So y naught I running from 1 to n, or n samples drawn from a box, the box is normally distributed. So I am going to get y naught of I running from 1 to n. So I have now copious supply n. What is n? N in principle could be a million if the vector x naught is of a size million, but even though the vector size may be million, I don't have the luxury of being able to pick large sample. So we cannot do large sample theory, we have to do finite sample theory, small sample theory. That is what we are going to be talking about. Now, so what did I have? I have the initial distribution, I have n members of the samples driven from a standard normal. I am now going to convert the standard normal ensemble members to the ensemble members from the initial distribution using the previous slide, the connection between x and y and x. So now I am going to introduce another symbol. So we will use x for the state, we are going to use xi for the ensemble. So xi 0 I hat. What does it mean? This is the at time 0 ith member of the initial ensemble, and also that's the hat represents it is the initial analysis ensemble. So that is equal to m naught. So what is m naught? I'm sorry, I'm going to say this is m naught to be consistent with this. So let that be m naught. M naught, the mean of the sample, plus s naught is the Cholesky factor times y naught I. Why does this make sense? Please go back to the slide here. The equation 3. The equation 3, what does it say? X is equal to mu plus Ly. If y is from unit normal, in order that x is from normal with mean mu and variance sigmas, I need to be able to transform y into L using an affine transformation mu plus Ly, where L is the Cholesky factor of sigma. I am using the same principle in here. S naught is the Cholesky factor of P naught, Y naught I is the ith member of the ensemble from the standard normal, M naught is the mean. So I have now created, n samples. Now look at this now. It could be very expensive to be able to create the samples because I am going to be dealing with a million dimensional system perhaps. So once I have created a sample, what is the initial mean? Initial analysis mean is x naught hat n, which is the sample mean of the initial ensemble. This one is equal to m naught plus s naught y naught of n. So if y naught of n is the sample mean of the y ensemble, x hat of n at the time 0 will be the sample mean of the initial ensemble. Now what is the basic property? Y is a standard normal, is a mean 0. So what is the claim? Y naught n hat, which is given by this, that tends to 0 as n tends to infinity. Why? Y's are the samples created from a standard normal with mean 0. So these are the properties. So what is the first thing we require for creating an ensemble? I first need to have a very good random number generator to generate n capital N samples of random vectors from the standard normal distribution. Once I have this, I can do this. Now what is involved in here? I have to do a matrix vector multiplication, then I have to do a vector addition, and this I have to repeat n times, and that relates to the total cost of computing the initial ensemble. So what does this initial ensemble give you? I have an estimate of the initial ensemble covariance, that is the analysis covariance of the initial time. You can see this is the ith ensemble member, that is the sample mean, ith ensemble members are the sample mean. You take the outer product of that, sum over n divided by n minus 1. So this is going to be the sample estimate of the analysis covariance at time 0. Analysis covariance at time 0. Now using the transformation, I can also rewrite the line 1 by line 2, and the quantity within the parenthesis as n goes to infinity goes to I. That is because what is the quantity in parenthesis? That is the sample estimate of the covariance of y. The actual covariance of y is I. So in time it will go to I. So the whole thing reduces to, for large sample, S naught times S naught transpose is equal to P naught. Therefore the analysis estimate, the estimate of the analysis covariance at time 0 converges to the actual covariance P naught as n the number of samples go to infinity. Why is these limits are important? I keep repeating this because the quantities calculated using ensemble members, ensemble statistics, there is a true statistics, there is always going to be a difference. The difference becomes smaller and smaller as the number of samples n becomes larger and larger. So if you cut the number of ensembles to be finite, let us say 100, 200, that is all your estimate is going to have an error, and that is the error you have to deal with. Why? Not because I want to, but because of the computational limitations. So it is not that I like to commit this error, but I don't know how else to do it because all the other approximations are approximations. Not only they are approximations, they are very expensive. For example, in the extended Kalman filter, if you look at the update for the forecast covariance, that still requires 2 matrix multiplications. Each matrix multiplication is going to cost you n cube. So even though it is approximate, it costs a lot of money to compute that approximation. So what is the idea of ensemble? If it is approximate, why to spend too much money? Can I compute an approximation in a quick and dirty way? Can I compute an approximation in the cheap way? That relates to the notion of ensemble ideas. So if I know how to create the initial ensemble, I can fast forward in time. So what is that now I can assume? I can assume the following. So let us assume at time k I have ensembles, forecast ensembles k I. So I'm sorry, these are the analysis ensemble. How it is analysis? Hat is analysis, superscript F is forecast. So let this be the analysis ensemble. So what is that? What did I have? This is time k. So I have analysis ensemble n of them. Each point of this is xi k I hat. Now so if xi k I hat is the analysis ensemble is related to the analysis mean through x hat kn, and the analysis covariance square root x hat k through y hat yk of I. So what is yk of I? So let's come back to this now. So let pk hat n be the analysis covariance approximation, as well as this is the analysis mean approximation. Pk hat can be expressed as the product of Cholesky factors sk hat and sk hat transpose. Therefore I know the mean, I know the Cholesky factor. I can also derive, I can also relate from the distribution, I can also relate the samples, the analysis sample to the standard normal distributions. Therefore yki are belonging to the standard normal distribution, and this formula is an important formula. This formula is the same as that one holds good at the initial time, except that k is equal to 0. If you put k is equal to 0, I get what I got. So if I can do it at initial time, I can assume I can do it at time k, because I have forwarded in time by induction. So I have created an initial ensemble. So this is what's called the initial ensemble. What is it? It is a swarm of points in the n-dimensional space. It's a swarm of n points, capital N points in the little n-dimensional space. So I have an analysis ensemble at time k. Now what do? I have to create a forecast ensemble for the next time. So I am going from time k to k plus 1. I have this analysis ensemble here. I would like to be able to create the forecast ensemble. What do? I take a particular analysis ensemble, which is xi hat k of I, run it through the model and get the forecast ensemble, which is xi k plus 1 I f. Hey, that's what it's going. Xi k I is the ith ensemble member at time k. By running it through the model m, I am going to get the forecast ensemble. So the forecast ensemble, the ith member of the forecast ensemble at time k plus 1 is obtained by taking the ith member of the analysis ensemble, running it through the model, plus adding a noise. Now let's talk about this now. Noise, you don't add the same noise to every ensemble member. You take, so what is wk plus 1i? Wk plus 1i is the ith realization of the model noise. So what is the model noise generator? This is the model noise generator, n0 qk. Out of that comes wk plus 1i. Wk plus 1i. Okay, so the forecast is random because of two things. One, the previous analysis is random. This is the additional randomness we are doing. Therefore, this is random. That's how I am trying to generate the forecast ensemble. So from the analysis ensemble at time k, I am creating the forecast ensemble at time k plus 1. In the standard nonlinear filter or the Kalman filter, there is only one mean, there is only one covariance. I am trying to update the mean, I am going to update the covariance. Updating the mean is not expensive, updating the covariance is very expensive. Let me remind you, in the classical Kalman filter, pk plus 1 f is equal to m times pk hat m transpose plus qk plus 1. In Kalman filter application, this is the real killer. Why? I have to do a matrix multiplication here, I have a matrix multiplication here, each one of them takes n cube time, each one of them takes n cube time, each one of them takes n cube time, O of n cube time, and n is of the order of million. We have already seen to do one matrix computation on a petaflop machine when n is a million, it will take about 11.5 to 12 days. So this step alone will take close to 24 days. Heck with it. We simply cannot, we simply don't have the time. We simply don't have the time. That's why we are looking for all kinds of ways to approximate, which I can do in my lifetime. So let me summarize the thing as given here. So at time k, I am given the analysis mean, I am given the analysis covariance, I am given the ensemble itself. Once I have ensemble, I can compute these quantities. I am now have run this analysis ensemble through the model and create the forecast ensemble. Once I have created the forecast ensemble, I can compute the forecast mean, I can compute the forecast covariance. This is what I was trying to tell you. So this is the outer product matrix. I am trying to add n outer product matrix, capital N. The size of this matrix is n by n, but I have only capital N samples. So the rank of pk plus 1 f at using n sample is no more than capital N. Capital N is much smaller. So by definition, you are dead on arrival. So what did we have? We always consider reduced rank. Computationally, these reduced rank matrices are ill conditioned matrices. You can't invert them, you can't do many things with them. So you have to be very clever in trying to do lots of things. And why do you want to settle for these kinds of crude approximations? Because for geophysical problem, these are the only things we can afford to do in today's technology. That's the bottom line. So I had analysis at time k, I had a forecast at time k plus 1, I have moved things forward. Now what do? I have to do a data simulation. So there are n forecast members. So let's go back and understand this now. So at time k plus 1, I have n forecast ensemble. A typical forecast ensemble is called xi k plus 1 if. I have only one observation, zk. Please remember zk is equal to h of xk plus vk. That is what is given to me. But we already know vk is normal with rk. So what is that we need to do? I have n members, n strands of the forecast. I have only one observation. I am not going to go into the details. If you assimilate the same observation on every strand of the forecast, your analysis covariance will be underestimated. So to avoid if the analysis covariance is underestimated, that will lead to divergence of the filter. Computationally, there will be major challenges and problems. So to avoid that, what do? We introduce the notion of what is called virtual observation. You get one observation zk. I am now going to create a set of virtual observations. What is zk plus 1i? Zk plus 1i is the ith version of the virtual observation, which is equal to the actual observation given by the satellite, radar, whatever it is, plus I am going to add to that an ith version of the observation noise. Please understand, zk1 already has some noise. I cannot separate zk1 from the noise because the noise is unavoidable and inseparable. But I do know the properties of the noise. So what is that we are trying to do? We are trying to generate another random number generator n0 rk. I am going to create a noise vector vki. So I have zk plus 1, vk plus 1i. I am going to add vk plus 1i to get the ith member of the virtual observation zki. This I runs from I is equal to 1 to n. Then what do? I simply apply the Kalman filter equation. So the analysis at time k plus 1 for the ith ensemble strand is equal to forecast at time k plus 1 the ith member plus k time zk plus 1 I minus hk plus 1 I zk plus 1 I. Here I would like to enlighten you with a couple of things. I am sure a careful reader would have already noticed it. Hey, you started with a nonlinear model, but you are using a formula that is meant for linear model. So this equation for the update for the data assimilation step, we are trying to do two things. We are not doing the actual observation, we are creating virtual observation. We are not doing any nonlinear thing, we are only doing a linear thing. And that should not be surprising to any one of you. Even though the model is linear, observations are linear, the estimates for the analysis is always a linear estimate. I want to bring that to focus. The models in the nonlinear filtering, what is that we have seen? The model is linear, the observations could be nonlinear. But what is the principle we are applying? Best linear estimate, blue. So the estimator has still a linear structure. That is why I am trying to use. So what is this? This is the estimate. This is the estimate of the analysis. This is the estimate of the forecast. Forecast plays the role of a background. Zki minus this term is the innovation. I am multiplying by a Kalman gain. So what is the rub here? How do you compute Kalman gain? So Kalman gain has to be, as you know, is dependent on the forecast covariance, the observational covariance, and the operator H. Operator H is very well known. The forecast covariance known only approximately. The observational error is known perfectly. So some are good, some are not good. So we have to combine good and bad to create what we want. So you can readily see K using the formula that we already know that mixes the forecast covariance. The forecast covariance is already approximate. So the K that is going to be used in here is also approximate. So that is another source of error. So let's try to talk about some of the aspects of analysis. So I have done the analysis using the expressions in page 10. I'm now computing the analysis statistics. Analysis mean is going to be given by this formula. If I substitute the expression from the previous, this is the virtual observation. The virtual observation, the mean of this are given by that. The covariance, in order to compute the covariance I have to compute the error. The error in the analysis is given by this. The error in the analysis has this structure. Look at this now. Vk plus 1 I is the ith member of the observational error. This is the mean of that. So this difference is the anomaly. That anomaly goes to 0 as n goes to infinity. So these are some of the things one has to remember when tries to manipulate these quantities. These quantities can be very small, but still we need to bulldoze all these small quantities. Therefore, I am now going to compute the analysis covariance. I am now going to compute the analysis covariance. The analysis covariance is given by this. I am now substituting the expressions for the analysis error for the ith ensemble member, which is then given by this expression, these expressions, which when simplified will become this, which when simplified will become this. So in this case I want you to remember Rk plus 1 n is the estimate of the analysis covariance. As n goes to infinity, that tends to Rk plus 1. So the other quantities follow readily from these expressions. I also want you to remember a couple of things. These are all coming from the observation noise. These are all coming from, this comes from the forecast. This comes from the observation noise. This comes from the observation noise, that is forecast. So you can see this is the cross covariance between the observation noise and the forecast, observation noise and the forecast. These are all finite samples. Now how do we know these finite samples make sense? In order to understand where if this finite sample approximation makes sense, I have to consider the asymptotic versions of these formulas. So what gives you the right to use the finite sample expressions with the errors? If we can show the errors in the estimate using finite samples go to 0 as n goes to infinity, that gives you a confidence. Yes, I know I am committing error, but I am committing error not because I wanted to, and this is the direct result of smaller number of samples. If I had the luxury of being able to go for a larger number of samples, all my errors will vanish, and that's a comfortable thought. That's the reason why we do asymptotics. Not because in practice asymptotic makes sense, but asymptotic analysis gives you a guarantee that when you do estimates with finite number of samples, you can think of being close to the truth, and how far you are close to the truth depends on the number of samples. So we have to go between asymptotic analysis versus finite sample analysis all the time, and statisticians do this very cleverly, better than anybody else. Therefore, I am now going to do some of the asymptotic analysis as I talked about. This term is the anomaly in the observation noise, and that tends to RK plus 1, which I have already alluded to. I also want you to remember one more, the cross term. What is this? Forecast error, I am sorry, the cross term, the second term, I am sorry, first term, second term, third term, fourth term. The third term and the fourth term in the slide, in slide 12, this term and this term involve the cross covariance. It can be shown that cross covariance, this is the cross covariance. What is the cross covariance? Let me bring this in. This is the forecast error of the ith ensemble. This is the anomaly of the ith realization of the observation noise. The cross covariance of that as n goes to infinity goes to 0. Therefore, in the previous slide, the third term and the fourth term, they automatically go to 0. Therefore, the expression for k, the Kalman gain, which I have postponed for this long, is given by the n sample approximation of pk plus 1 f. Now look at this now. Xi ki f, xi ki hat, these are all ith member of the forecast and analysis. But when it comes to question of pkf, I am going to have an estimate, I am going to put a n. If I am going to have pkn hat n. So what are these? These are n sample estimate based on n sample estimate. N sample estimate, because I want to be able to distinguish between. So if I say pkf, that is the actual forecast covariance. If I say pk hat, that is the actual analysis covariance. If I attach a n in the stomach to them, that is an estimate. So this is the n sample estimate of the forecast covariance, hk plus 1 transpose. This is the same formula as comes from linear analysis. This product, again we understand these two are the same quantities, ensemble approximation and RK plus 1. RK plus 1 we already know. Look at this now. I would like to talk about it a little bit further now. RK we are assuming is full rank. PFK plus 1, that is low rank. HK we are assuming full rank. So the product of this is low rank, but I am adding a low rank to a full rank matrix and getting the inverse. Does the inverse exist? Yes. Who guarantees the inverse exists? Sherman-Morrison-Woodbury formula. So what is that you can consider this? I am having a low rank perturbation of a full rank matrix. So this inverse can be shown to exist, and using this I can compute k. So k is an approximation. So k is an approximation. So what is the actual data assimilation step? That is on page 10. I want to revisit that in the light of these calculations. So I have now calculated k. If I have calculated k, I know the ith virtual observation, I know everything, I can compute the analysis ensemble. If I can compute the analysis ensemble, I can compute the analysis mean and analysis forecast. So let us talk and the analysis covariance. So let us assume two things now. So what do these centers do? They have a large code that are representing the model. They run this model code parallel for n initial condition. N is 50, 100. I don't think in the world anybody runs large models using more than 200 ensembles. Nobody. It is not because they don't know, it is simply because they don't have the computing power. Why? Let us talk about this now. You have to make daily forecast. You have to make forecast every day. Every day you make forecast for 1 day in advance, 2 days in advance, 3 days in advance, 5 days in advance, 6 days in advance, 7 days in advance. And you keep doing this every day. So you have only 24 hours maximum time that is possible to you. Of the 24 hours, the observation people have to collect all the observations from radar, from satellites, and bring them all to a common platform. The modelers have to run the model forward in time, 50 ensemble or 100 ensemble. The modelers give the model output, the observation people give the observation, then the data simulation person comes to work. The data simulation person does not come to work until and unless all the observations are made available, unless all the model runs are available. At that time he takes both and he tries to create this analysis ensemble. Once he creates the analysis ensemble, he can create the analysis mean, analysis covariance. It is this analysis mean, analysis covariance for 1 day, 2 day, 3 day, 5 day is being announced as a forecast product. So what will be the time available for modelers? Let us say 6 hours. What will be the time available for all the observation people to get the observation on board? Maybe 12 hours. How much time a data simulation may have? 6 hours, 8 hours. So you have to finish all these things in a fixed number of hours, and one has to depend on the other. The data simulation person is the last one who comes to work. So if you divvy up the 24 hours into these 3 parts, you can see how the operational centers are busy. They don't waste an iota of a second, and that is what happens in all the major forecasting centers such as Ensemble in Washington DC, ECMWF or British Met Office, Japanese Meteorological Agency, I am sure Indian Meteorological Agency, they also do that depending on what kind of a forecasting system, data simulation system they have assimilated and what kind of computers they have. I hope I have made it clear to you as to how the data simulation is done within the context of Ensemble. So some comments. When n is small, n is always small, not when n is small. The cross product terms, you remember earlier, they will not be close to 0. That means there will be a large error in the estimate of the n sample estimate of the forecast covariance is going to be in error. Forecast covariance error directly reflects into Kalman gain error. So that is something I want you to be cognizant of. That error goes to 0 only when number of samples becomes large. I also want to talk about one more, the covariance matrix for forecast. Forecast covariance is the bottleneck in Kalman filtering. So this is the Jacobian times pk hat, Jacobian times pk hat when n is equal to 1. So when n is equal to 1 million, if I am using 100 samples, the rank of pkn is no more than n, which is less than n, therefore reduce rank. I am trying to reinforce all these things by quantifying some examples. Now please understand, this itself is an approximation. Even the approximation costs money. I have already alluded to this. I have then the DMXK is not available. DMXK is a million by million matrix. I only know the analysis. I have to evaluate the elements of the million by million matrix along the trajectory. So that is another hidden cost that does not come out. That does not come out. But so in the case of covariance approximation, I am sorry, in the case of first order filter or second order filter, So the pK has full rank in first order and second order filter. Therefore, it is a full rank, but it is still approximate. But full rank but not exact, it is only approximate. So I would like you to keep all these things at the back of the mind. And I am also now going to argue why we need virtual observations. I have already alluded to that. If you use the actual observation instead of the virtual observation, you would use only one observation for every ensemble. If you compute the analysis error, term for the analysis error becomes this. When you compute the analysis error, it becomes this, and the analysis covariance matrix computed using this becomes this given by this expression. We have already discussed all these things very much in detail in our book, but I would like to tell you that the analysis covariance term is given by this, and it does not have the KR-KT term in it, and this lack of KR-KT term in it leads to underestimation, and if the analysis error is the analysis covariance underestimated, forecast covariance is also underestimated, because forecast covariance depends on the analysis covariance. That is the reason why we use virtual observation, to be able to make up for this deficiency in resulting in underestimation. Okay, when ensemble filter was known as the Monte Carlo method of estimating Kalman filters for nonlinear systems within the control theory literature as early as 1960s, but it was invented by Evanson in the mid 90s within the context of geophysical applications. So within the context of geophysical application, the person who made this ensemble approach popular is a Norwegian geophysical scientist, Evanson. I think G. Evanson, around 1995, approximately thereof. Approximately thereof. So ever since the ensemble methods have become popular, most of the centers have gone for this. When originally Evanson published the paper, he did not use the virtual observation. People who came after him quickly realized that if you used only the same observation to every ensemble strand, your system leads to an underestimation. Underestimation leads to numerical difficulties. So to be able to prevent such numerical difficulties from arising, an artificial method was created, and that is what virtual observation is all about. So it is simply a mathematical trick by which I can restore some sanity in the world where everything is approximate. What is the next idea? Some might say, hey, instead of trying to modify the observation, why don't we simply change the Kalman gain such that I don't have to mess with the observations. Why messing with the observation is considered bad in some circle? Observation is given by Mother Nature. Mother Nature is observed only through observation, and why to corrupt what Mother Nature tells us? So philosophically, some people are opposed to creating virtual observation because it is not philosophically consistent, meddling with what Mother Nature is telling us. Therefore, what is it they were looking for? They were looking for an alternate approach. And what is the alternate approach depends on? This alternate approach depends on the following. I have the analysis ith ensemble, I have the forecast ith ensemble, I have the innovation. Please remember, I am using the same observation. While using the same observation, can I use another weight W such that I can restore sanity in the analysis ensemble? That is a very beautiful mathematical question. This question was answered in the affirmative. There are several classes of ensemble filters. They came out as a result of this line of questioning. So the line of doing the simulation using virtual observation is called stochastic method. The line where you use a single the same only one observation but change the weight, that is called a deterministic methods. So deterministic methods of implementing ensemble filters, stochastic methods for implementing ensemble method. Stochastic method relies on creating the virtual observation. What is the advantage of it? You simply create a virtual observation, you are done, you can close the eyes and then say, hey, I have a decent approximation limited only by the value of n. In here I have to do a little bit of more calculation, but I do not have to mess with the observation. Observations are word of God. That's essentially the kind of approach that's taken here. So that's the approach of how do we modify the Kalman gain instead of the observation. So this is the, so if this is the analysis ensemble, this is the mean of the analysis ensemble. If I know the analysis ensemble and its mean, I can compute the analysis error anomaly. If I can compute the analysis error, I can compute the analysis covariance by this expression. Please remember, I am now talking like a broken record. I'm following the same path, but with a different criterion for mixing the forecast information and the innovation information. So W, the matrix, I am now going to change the Kalman gain to suit what I want without having to generate virtual observations. Therefore, if the error structure is given by this, the posterior covariance, which is the analysis covariance, is given by this expression, Let us assume the forecast covariance has a square root factorization like that, has a square root. So this is the forecast covariance. So this is the forecast covariance. Let us pretend this forecast covariance has a square root factorization available. In that case, by combining these two, I get by replacing this by the square root, I get the analysis covariance is given by the product of this times that. You can readily see that. I believe there must be a parenthesis then here. Sorry, there must be there's a parenthesis here. There must be a parenthesis there, and then there must be a parenthesis here with that. That's correct, because I minus W S transpose, I minus W times S transpose to the whole thing. That's correct. Yeah, parenthesis is missing here. Please add that. So with that, the question is how to choose W. I am going to quickly talk about the method for choosing W. This idea in electrical engineering systems literature as early as 1968. It was reinvented in the meteorological community in the late 90s after Evanson put forth his ideas. It is very hard to tell how much they knew of the previous literature, but anyway, they have been reinvented. So this is the analysis covariance, the forecast covariance minus this. You may remember this from the classical Kalman filtering equations. So what is the basic idea? I would like to be able to simply factorize. And why do I want to talk about factorization? There is a close connection between covariance square root implementations and reduced rank ensemble implementation. They are very nearly related. And so if I have a Cholesky factorization, I am now going to call A is equal to H times SF transpose. So I am now going to factor the forecast covariance. I am going to define a new quantity. So this is the forecast covariance factorization. This is the new quantity A I am going to introduce. With these changes in notation, this p hat. So what is that I am now trying to do? I am trying to drop the time index, drop the time index. Why? Drop the subscripts. I don't want to clobber my expressions because this is all happening at a given time. So I don't have to remind myself and bulldoze all the subscripts together. So by drop the subscripts from the covariance matrices. Therefore, p hat is product of the square roots plus this expression. So these two expressions are essentially one and the same. This is the covariance version, this is the square root version, covariance square root version. Covariance square root version, and with this square root version the expression becomes this, and that can be written as this expression after simple matrix algebra. Now what do I want to do? I would like to be able to factorize the one that is within the square bracket in here, and that is what the factorization is to be done. I would like to remind you now, the pk plus 1 hat becomes this, and now that has been expressed this way. I would like to be able to, so if the forecast covariance can be expressed as the square root form, analysis covariance also must be expressible in the square root form. If I express the analysis covariance in the square root form, I can identify W, the quantity that I need, very easily. So let A transpose, let this be the square root of, look at this now, I am using several different symbols. There are lots of quantities involved in here. SF, S hat, S. This is the square root of the forecast covariance. This is the square root of the analysis covariance. S is the square root of is a generic square root. I am going to use the generic square root in order to be able to define the square root of the quantity. This quantity, sorry, I am going to define the square root of that quantity, this quantity. So this is the matrix. A is the matrix. A transpose A is a Gramian. A transpose A plus R is a symmetric matrix. Let this be the square root of that, that is generic. Let R be FF transpose. Therefore, the inverse of this is the inverse of this, which is given by the inverse of that. And I am now going to consider a matrix of this type. I already know the square root of A transpose A plus R given by that. I am going to substitute this using this. Now I am going to multiply and divide. So what is that we can do? If I am A is equal to A plus B minus B, I can add and subtract. A is equal to A times B divided B, I can multiply and divide. These are standard tricks in mathematics to create newer expressions. So what is that I am now trying to do? I am trying to multiply the inverse and the matrix, the transpose and its inverse. So I am simply trying to do multiply and divide. If I multiply and divide, I get an expression. That expression when simplified becomes this. See the following slides for the details. So the simplifications are given in here. Using this simplification, now I can substitute and verify, but my analysis covariance are timed. Yes, I know I am going a little fast, but I want you to be patiently look through this. These are grunt. This is all grunt work from matrix algebra, and if you want to be thorough in understanding data assimilation method, you have to be ready for this grunt work. Making you ready for the grunt work is part of the aims of these lectures. Therefore, this is the original expression. By substituting the factorized expression from the previous one, I get this. Now what do I want? So this is the expression I get from Kalman filter. This is the expression I get. I want these two to be equal. If I equate these two, everybody but W are known. So I'm computing the same quantity in two different ways. If I compute the same quantity two different ways, they are equal. So by equating these two, so this expression and this expressions are equal. One expression has a W, other expression does not have a W. The W expression is the new way of deriving, the one without expression is the classical way of deriving. So what is our aim? I want to change the Kalman gain, but I do not want to change the result. So how do I use W and still enforce the same result as I would have gotten had I used the standard Kalman gain without having to use the virtual observation. So that gave rise to an expression for W, which is given by this, Therefore, if you use this W as a new Kalman gain in our analysis step. Let me go back. In our analysis step in page 17, I will get the same result as Kalman, but without having to worry about the virtual observations. So this corresponds to the deterministic approach to Kalman ensemble based ideas, ensemble filters. Some people call it ensemble filters, some people call ensemble Kalman filters. I think it is misnomer to call it ensemble Kalman filter, because classically Kalman filter refers to LQG. Here nothing is LQ, nothing is L, everything could be in general linear. So within the context of meteorology, we use my preferred way of telling or explaining this is, it is simply an ensemble filter or a reduced rank filter. Okay. Now, is ensemble filter equal to reduced rank filters? No. There are a million ways in which one can create a reduced rank filter. Ensemble method is one version of trying to create a reduced rank filters. So in my view, reduced rank filters is a larger class of filtering mechanisms where we deal with approximations of different degrees. Ensemble methods is simply one way of being able to create such approximations meaningfully by simply running the model forward in time. So what is the basic thing in here? If I have the muscle power to be able to run the model in parallel 1000 times, I am better off. But there is no brain power involved, there is simple statistics. So by trading muscle power for the brain power, ensemble methods rests on making quick simple estimates. Of course there are nuances. Do I do virtual observation? Do I do other things? So but in principle, the totality, the amount of computation that one has to make in ensemble methods is simply dominated by the time required for model runs. That is where parallel computers come into being. Do you make 200 runs of the same model starting from different initial condition on the same computer? No. The technology has provided very powerful supercomputers which consists of several individual units. So what is that you do? In the world, they have large parallel computers. They can copy the model code into many of these computers and let all the computers run at near synchronous speed starting from different initial conditions. So by exploiting the parallel computing technology, by combining it with the ensemble methodology, in modern days we can create very meaningful forecasts based on data simulation techniques, and this is becoming one of the major workhorse in the forecasting industry, especially in weather forecasting all around the world. The British Met Office spearheaded this. Ensemble is following this. Meteor France, Japanese Meteorological Agency, and many of these places they have a research unit as well as a production unit. They all work together in conjunction. While they run the old version, they are also trying to bring in the new codes. For some time they run both the systems in parallel to be able to test it. Once the ensemble methods are well validated, then they slowly provide a sunset class for the old methods, and the new methods take hold in trying to generate daily forecast. That's the present situation. If you want to know more details about this, you can refer to the papers by Whittaker and Hamill. You can also refer to the paper by Tippett. Reference to all these papers are available in our textbook. We have a rather extensive annotations to the literature. Let P be a number in between 1 and n. N is the dimensionality of the state space. So if P is less than n, I am going to be talking about pth order reduced rank implementation of square root versions of the covariance filters. Mouth is full. So we are seeking a rank P square root filters. What is the use of square root? Square root filter generally improve condition number. Condition number improves the quality of the numerical computation. Reduced rank in generally reduces the computational cost. Why the computational cost? You can readily see that if the dimension is large, the cost is large. So you can think of it as a kind of a reduction largely induced by the desire to reduce the computation cost as well as an advantage to improve the condition number. So what is that we do? Let us talk about the initialization stage. That is the mean, that is the covariance. Let V be the matrix, let V be the eigenvectors of P naught corresponding to the eigenvalues lambda 1, lambda n. So lambda I, Vi are the pair. I can collate all the eigenvectors into a matrix V. I can collate all the eigenvalues along the diagonal and call it a matrix lambda. So this is the classical eigenvalue decomposition, which can be written like this, since we already know V transpose is equal to V transpose V is equal to I. I do not know how many times we have seen this eigenvalue decomposition. It is very fundamental. We have also seen there are methods for finding square root. One is using Cholesky, another is using eigenvalue decomposition. So here I am interested in reduced rank. I am using eigenvalue decomposition. So I am using eigenvalue decomposition as a tool to implement reduced rank approximations. So that is the pathway. So I can express lambda is equal to lambda square root of lambda times square root of lambda. Then I can associate this like this. I am going to call S naught transpose, where S naught is given by this. Therefore P naught is equal to S naught transpose is the full square root factorization, where S naught is one factor, S naught transpose is another factor. These two factorizations, even though it looks like the Cholesky factorization, I obtained S naught not as a Cholesky factor, but as a product of V and lambda to the power half. I want you to recognize this is a different way of doing factorization. So far no approximation. Now I would like to be able to come to the approximation. We have ordered the eigenvalues in the decreasing order. So let us pick the top P values of the eigenvalues and corresponding top P eigenvectors V1 to Vp, lambda 1 to lambda p. Why is that? We have already alluded to this, I will say it again. The trace of, if P is a covariance matrix, trace of P is equal to total variance in all the components, and the total variance is summation lambda I is equal to 1 to n. If the lambdas are distributed as fast decreasing, see what are the various ways in which lambda can occur. For some matrices lambda can be flat like that, for some matrices lambda can decrease like that. So 1, 2, 3 n. So this is the case we are interested in, the bottom one. If the lambdas decrease very fast, I can pick a P such that summation lambda I is equal to 1 to P divided by summation lambda I is equal to 1 to n is greater than 90%. So what does it mean? The first P components together can explain 90% of the overall total variance that is hidden in the system. So it's a 90% accurate approximation. It could be 85% approximation, it will be 99.9% approximation. So you decide the level of approximation you are willing to contend with. Given that level 90, 80, 99, I can compute a P that corresponds to this inequality. The sum of the first P eigenvalues to the total sum of all the eigenvalues is greater than or equal to a previously accepted threshold of 80%, 90%, 99%. So that is how I am going to pick a P. Now if on the other hand the eigenvalues grows decay very slowly, what does it mean? You may have to have the entire eigenvalue system. The P may be very close to n. So in this case 1, this case is 2, I am considering the case 1. In the case 2 you may not be able to reduce the rank by simply chopping off the last one, because even the last eigenvalue may be very large. So it all depends on the intrinsic properties of the eigensystem of the associated covariance matrices. So I am now going to assume my associated system has a picture which is very similar to the curve 1. So if I do that, S naught, please go back to in the previous one. What is S naught? S naught is a n by n matrix. Is a n by n matrix. I am going to keep the first p columns of it and drop the last n minus p columns. So the matrix, sorry. So the matrix that is built out of the first p columns of S naught is now going to be called S naught 1 colon p. So the matrix n by p matrix consisting of the first p columns of S naught of the p dominant modes. What do you mean by dominant modes? The eigenvalues are the larger. The one that I am dropping together, the total sum is less than 10%, is less than 5%, is less than 1%. So I am trying to divide the eigensystem into dominant modes and not that dominant a mode. I am simply collecting all the dominant modes together. In that case, I can take this S naught 1 colon p and S naught transpose 1 colon p for some p in the range 1 to p. I can approximate by p naught by that. So what is this? This is the rank p approximation of p naught. So what is that we are now going to do? We are going to initialize a reduced rank square root filter with the mean m. Instead of the full covariance, I am going to be talking about, instead of the full initial covariance square root, I am going to be talking about the first p dominant modes of the covariance square root. I hope you see the difference. This is a very beautiful idea. So now I am going to create a forecast. So what is the forecast covariance? 1 to p. The forecast covariance 1 to p. I am now going to talk about an expression for this. This is the full rank forecast covariance. This pk has a square root implementation like this, and this has a square root implementation like this. This I can rewrite it as sk plus 1f and sk plus 1f transpose, where sk plus 1f is given by this, and that is or n by 2n. We talked about already the expansion part in the last lecture when we talked about covariance square root implementation. So recall, we do not know sk bar. We do not know sk bar because we do not know the full, but only the rank p approximation of sk bar. So that is the important thing. We have been satisfied with the rank p approximation. So if I so that's the basic aspect of it. We also know, so one more, this is the, I'm sorry, this is the square root of the model noise covariance. We may only know the rank q of this. So this may be, so I may only know the rank q of this, I may only the rank p of this. So I have to deal with a rank p approximation here. I have to deal with a rank p approximation here and a rank q approximation in here. So totally this matrix sk plus 1 it becomes a matrix of size n by p plus q, the reduced rank approximation. But our calculations are always rank p. So how do you reduce a matrix of size n by n plus p to a n by p matrix? That is what is called the reduction. This reduction can be easily implemented by, so this is what is called the rank reduction process. Sorry, this is what is called the rank reduction process. The rank reduction process depends on whether p plus q is less than n or p plus q is greater than n. P is the rank of the analysis covariance matrix, q is the rank of the square root of the process noise. P plus q are two integers, p and q are two integers, so p plus q could be less than n or greater than n. I am going to consider case A where p plus q is less than n. So what is that we are going to do? We are going to fall back on singular value decomposition. Now you know why we did all the singular value decomposition at great length, why we did Cholesky decomposition at great length, we did eigenvalue decomposition at great length. Why? If you understand these matrix methodology very well, the underlying basic principles of matrix algorithm, they are used repeatedly in any advanced methods for dynamic data simulation, and data simulation in a stochastic context are in general advanced methods, and that is where we use repeatedly several of the algorithms from matrix theory. So what is the step 1? The step 1 is so we already have a matrix which is n by n plus p plus q. Let V be this matrix, be an orthonormal matrix of eigenvectors of sk plus 1 times sk plus 1 transpose sk plus 1. We are essentially doing the same singular value decomposition. Please remember that. I would like to relate some basic ideas. In our static case, we had H is equal to m by n. So we had two kinds of Hessian matrix, Gramian matrix, H transpose H and H transpose. By doing an eigenvalue decomposition of this, I derived an eigenvalue decomposition of this of the other one using SVD. The same principle is applied here, but H is replaced by H is going to be replaced by the matrix S k plus 1 is the matrix that we have defined in the previous page. Sk plus 1 defined in page 25 is this matrix. So by replacing H by Sk plus 1, I can do all the analysis that I did for H, which are mathematically similar. So by doing the eigenvector eigenvalue decomposition for this Gramian, let these be the eigenvalues, let this be the eigenvalue decomposition. So once I know this, once I know the eigenvalue decomposition of H transpose H, I can derive the eigenvalue decomposition of H transpose using SVD, and that is exactly what I am trying to do. I have already known the eigenvalue decomposition. I have already known the eigenvalue decomposition of xk plus 1 transpose xk plus 1. So I am now going to talk about xk plus 1 times xk plus 1 transpose from here to here using the standard rule of SVD. So these two matrices by theory have the same set of non-zero eigenvalues. I can define a matrix like this, matrix of eigenvectors of that. If I multiply these two, I get this. From there you can readily verify that one. Therefore the matrix V, which is defined in here, the first p columns of that matrix are the so this is the whole matrix. This is the first p columns of this matrix. It can be shown that these two matrix relations is the rank p approximation. So the rank p approximation matrix for the forecast I want is given by multiplying Sk plus 1, which I already have, which is a matrix of size n by p plus q, by this. So this is the required rank p approximation. Case B is similar. I do not want to go over the detail by reciting the whole thing. I would leave the case 2 as an exercise for you. That means I can do the same reduction in the rank by this process. Now I am going to come back to the data simulation step, the last step in this process of reduced rank implementation. So the data simulation step, this is very similar to the full rank approximation, very similar to the full rank counterpart. I do not have to say in counterpart in Kalman filter, square root version. Square root version. So I am going to summarize the algorithm. Compute A. H is known, Sk plus 1 F is known, that is a square root, rank P square root. Now if you make P is equal to n, I get the complete full rank filter. If you pick P to be anything in between 1 and n, I get the reduced rank filter. So this algorithm is so beautiful. You can, by bellowing in and out the value of P, you get quite a variety of approximation. So this algorithm gives you not one approximation but a family approximation. The family essentially parameterized by the value of P, and P lies in the interval 1 to n. So depending on how much money you can afford to spend, depending on how much accuracy you want, depending on contingent on the properties of the behavior of the eigenvalues, you can create a wide family of approximations. So you can compute this matrix, then you compute B, you compute C. We have already seen these calculations in the context of Potter's implementation of the square root covariance filter. So C also covariance square root filters in the similar thing arises. We do exactly the same kind of computations. So I can now give an expression for a reduced rank approximation to Kalman gain. If I have a reduced rank approximation to the Kalman gain, I have a reduced rank update. Please understand, here I am using only one observation because there is no ensemble in here. It is simply a deterministic reduced rank implementation as opposed to ensemble methods for reduced rank implementation, which could be either stochastic or deterministic. So the rank P square root of Pk plus 1 is given by this, which is given by C, and this is the end result. So I have gone from a forecast step to the analysis step. So that completes the cycle in the computation of the filtering equations. This material is derived from chapter 30 of our book, where we discuss many of these things in great detail. Yes, the analysis of case B, I did not do it explicitly, but it simply involves some other types of matrix manipulations. The matrix algebra is the key in here. So with this, what is that we have accomplished? We have accomplished quite a few methods for doing data assimilation in stochastic dynamic models. In a stochastic dynamic model can be linear, nonlinear. The stochastic dynamic model may have model errors. The model errors are always represented by stochastic noise. That is the weakest link in this process. If I know the model error, if I know how to correct the model error, I would have corrected the model error. So the corrected model does not have as much error as the uncorrected model. So when do you consider model error to be random? I have an easy feeling that I have not incorporated several small scale processes. And when does that small scale processes you neglect? Suppose you discretize a primitive equation model on a grid. We all know from basic theorem in sampling that with a given grid length of size delta x, I cannot create samples of frequencies more than whose wavelength is related to more than less than twice the sample size. Twice the grid length. So sampling theorem essentially tells you when you try to discretize a continuous quantity, you may be missing out on high frequency or lower wavelength terms. So the primitive equation model covers the whole spectrum of processes. When you discretize it, I truncate, I can resolve only frequencies up to a particular level. We cannot resolve processes involving higher frequencies. Therefore, we have some idea that the neglected terms are high frequency terms. So one way to approximate the unknown high frequency term is to add a random noise. One way to approximate this is add a white noise. So white noise, addition of white noise to compensate the model error is largely a reflection of our belief that I have captured all the low frequency processes involved. It is the high frequency things I am not able to capture because of the finiteness of the grid size. So that is the credence that one can bring to bear for adding a stochastic noise such as white noise to the model error. Observations have always errors. So we have quite a variety of data assimilation problems. These problems were solved by Kalman in 1960, Kalman and Busey in 1961. Kalman did it in discrete time. Kalman and Busey did it in Kalman did it in discrete time. Kalman and Busey did it in continuous time. The discrete time derivation was perfect. The continuous time derivations used lots of heuristic principles of taking limits. it was soon realized the only way to derive mathematically kosher derivation for these nonlinear filters is within the framework of what's called stochastic calculus or Ito calculus. So there is a parallel development of nonlinear filtering within the stochastic calculus, stochastic modeling literature. For reasons that we don't have background in stochastic calculus, we restricted ourselves only to discrete time. We have given you the LQG problem complete solution Kalman filter. We have given a complete solution to the discrete time nonlinear model, nonlinear observation, nonlinear filter equations. We have given several different types of full rank approximation using 0th rank, 1st rank and 2nd rank filters. Then we talked about approximate reduced rank filters. We talked about reduced rank filters coming out of ensemble methods. There itself we have two versions, one by using random or virtual observation, another one is by changing a deterministic gain which is different from Kalman filters. We also talked about deterministic reduced rank implementations of covariance square root based filters. So I am assuming that this gives you the breadth and depth of the literature has come to be called filtering within the context of data simulation. So the Kalman filter, even though the ideas were known as early as 1970, by 1969, 1970 the entire problem of nonlinear nonlinear filtering in continuous time using stochastic calculus was thoroughly done, understood. So they have put the problem is essentially solved, but implementation of those continuous time ideas still is a big challenge. In principle, nonlinear problems, whether you attack it through continuous time formulation or discrete time formulation, continues to be a challenge in the computational world. With that, we conclude our discussion of data simulation using nonlinear filtering techniques. Thank you.